welcome everybody. It is my pleasure to introduce today Yang-Ming Tong. He is a PhD student at Georgia Tech, a computer architect that focuses on the intersection of AI and cryptography. And today he's gonna present the talk titled Cross, Leveraging AI ASICs for Homomorphic Encryption. Yang-Ming, the floor is yours.
Thank you so much for the introduction. And then today, I'm super thrilled to in front of the cryptographic prestigious experts in the field. And I'm gonna introducing two lines of my work, Cross and a gift, Morph, which is recently accepted at the Automation Conference this year. So before we get started, let me briefly introduce who I am and what I work on, and specifically my research overview. I'm a computer architect, and I'm focusing on enabling AI systems for cryptography. And I'm currently a fifth-year PhD at Computer Science of Georgia Tech, and luckily advised by Dr. Tusha Krishna. And I'm mainly known for developing two projects, and one is Cross, and what I got to talk about today. The another one is a reconfigurable AI systems that make AI to reconfigure itself to be a dedicated ASIC for different workloads. And I got to give tutorial for both of them in the upcoming ASPLUS 2026 at Pittsburgh. So if anybody come by, feel free to say hi to me, and we will invite you guys to there so that we will have a great audience in elevating the overall level. And this work gave me the machine learning and ML Commons writing star and a couple other sources. So overall, my research could be captured by this single slide. I design systems for AI and cryptography. Today, AI systems take data and model in the raw format. So we have this particular number one workload. And this paradigm cannot support private data like genome or closed source private model like ChatGPT, because this naive raw format of the data will leakage everything. And to protect the privacy, private data and model could be encrypted and then go through encrypted computation. And this is enabled by homomorphic encryption. And to support both raw computation as well as encrypted computation, I have built a system scheduler called Sushi and a compilation framework called Cross. And both lowering these two lines of workloads into unified sets of linear algebra. And this linear algebra will include matrix multiplication, vector arithmetic, and memory reorganization. And this unified of linear algebra could directly run on today's AI system, such as Google's TPU, Amazon Trainium, NVIDIA's GPU, as well as Microsoft MIA. And to study the performance of this AI system running on this workload, we built a simulator called SkillSim. And within the SkillSim, we could model the architecture of different today's AI system power. And then it reveals a key insight. That is, when the workload has various shapes, for example, matrix multiplication comes with different shapes, and they might underutilize the available computation in the given AI hours. And therefore, to make it more performant for a wide range of workloads of different shapes, I designed two lines of reconfigurable AI systems. And these reconfigurable AI systems could reconfigure their data paths as well as memory layout for each individual workload. And this could enable them to achieve full compute utilization under workload of all shapes. And further, to enable this automation compilation, I built a layout loop framework. And layout loop could search the optimal data flow and layout for individual workload. Among this work, Sushi has won the Qualcomm Innovation Fellowship, and Cross has deployed in Google and won the second place in University Demo at Design Automation Conference last year. It also won the GT Next Award and Startup Launch. Further, Layout Loop has been integrated into NVIDIA NV Labs, and the fact is a collaboration work with IBM. So let's first, with this as an overmind, and go through this overview today. And today, I'm going to cover how do we using existing AI systems to accelerate cryptographic applications. So we start with AI model, because AI model is the most common workload in today's data center. So we're using their computation demand as unit and using their latency as unit. So we will have three lines of cryptographic application. First, privacy presuming AI, which use homomorphic encryption to encrypt both data as well as the model to provide holistic privacy guarantee. Second, cryptocurrency. It relies on zero-knowledge proof primitives to offer both encryption and verification. And third, applying zero-knowledge proof encrypted AI computing will give us a verifiable encrypted computation. All these applications will increase the computational demand and latency exponentially. And in this talk, I will very thrilled to demonstrate you two lines of work, cross and morph, which could lower this exponentially increased latency to roughly superlinear. Let's start with cross first. And cross is a joint work with Georgia Tech, Google, MIT, and Cornell. And we want to give a special credits and appreciation to the Professor Alban, who have been able to see this work published before he passed away. So, but we are super appreciative and appreciative for his support and insights. So this cross is the #1 work, which enables AI ASIC for homomorphic encryption. They give you immediate serving of the homomorphic encryption in real time under Google's TPU. So what do we do? Let's start with the background. The reason why we're starting with this new generation of HE accelerator on today's AI system come from AI's new industry revolution. Specifically, artificial intelligence is driving a new industry revolution. It could transform chatbot, robotics, autonomous vehicle, AI coder, biology, protein discovery, and AI factory, all into digital tokens. In other words, the entire world is being digitalized and tokenized for AI assistance. However, such revolution has been blocked by the privacy concern. For example, Samsung has banned ChatGPT among employees after they see the code leakage. Grok accidentally released the user's conversation through a public search tool. And this is 3 years back. We delayed the AI features just because we want to keep the user data on device for review later. So these ones protect the privacy into a paramount requirement before we release the AI feature. And that gave us the following question: how to protect the privacy of both model and user data? To answer this question, we need to understand where this privacy concern come from. First, from model side, today's most advanced models such as ChatGPT or Anthropic's Cloud and also Perplexity, these models are proprietary. And their training data as well as their data analytic tools are all closed source. These closed source services cannot share all of their own boundary. This creating the right-hand side model privacy boundary shown in red. On the data side, we see the data from healthcare, finance, and government are also private data. And these data never able to leave their agency as well. And this creating the left-hand side orange data privacy boundary. Such two-sides boundary creates the significant privacy gap to use the right-hand side private model to serve the left-hand side private data. And as we all know here, homomorphic encryption could protect the privacy by enable directly computation on the encrypted data. So we could encrypt your model, set it to the untrusted infrastructure, and encrypt your private input locally within the data privacy boundary, and only send out the encrypted ciphertext so that within this untrusted infrastructure, we could using this encrypted model to serve this encrypted input to generating encrypted results. And these results will come back to the user, and only the user who has a secret key could decrypt it and gain a meaningful value. This is great, but because it secures everything, but it is very slow. And we all know the slowness comes from both compute and memory overhead. If we take the Resnet 18 as an example, encryption will boost it by 8,000 times and compute by 800 times. And this combined will lead into a 10,000x slower latency. And that make it impractical. As past few years, entire community has focusing on designing new hardware and compilation toolchains to reduce this growing complexity. And with few examples shown in the middle. But building these new chips and new compilation flow will take years of time and take a lot of money. And that's why we didn't see a available product for people to use today. And therefore, at this project, we want to enable immediate HE acceleration. So we're using existing AI ASICs, such as Google's tensor processing unit, to accelerate homomorphic encryption instead of building new hardwares. And we build a transpiler, means we converting the encrypted data into kernels that run very efficiently on today's AI ASIC, which we'll cover in this talk. And it could lowering the years of time into immediate, and then saves you millions of dollars because we don't need to fabricate any new hardware. Now it comes to a fundamental question. Why we use AI ASICs, such as Google's TPU, instead of other commodity hardwares like GPU? To answer that question, let's deep dive into this TPU to see why it has. In the high level, it gives you better performance per watt. We categorize various chips shown on the right figure, where the horizontal axis indicating the power, where the vertical axis indicating the throughput. So in this right-hand side throughput power plot, the diagonal line means throughput divided by power, or so-called power per watt or energy efficiency. And upper left means better. And further, we categorize each chip based on their technology node. For example, the light blue indicating the 7 nanometer, and the light yellow means 4, 5, 6 nanometer, and green means the advanced technology node, such as 3 nanometer or even below it. As you can see, AI ASICs always give better performance per watt than other commodity hardwares like GPUs and FPGAs. And this enables more chip to be fit in within the data center. And they give you higher throughput at scale. With this strong motivation, let's now deep dive into what a AI ASIC such as Google TPU look like. In the high level, tensor processing unit from Google TPU give you 3 features: significant memory, significant model compute, as well as wide range of the reordering. Let's start with the memory. TPU has massive memory. First, different generation of TPU has hundreds of gigabytes of HBM and hundreds of megabytes last level cache. Of course, go ahead.
So, you can't buy these TPUs, right? These are totally closed by Google. Isn't that right?
Now, before 2 years ago, that is the truth. And now people has officially enabled this leader AI company to buy it. For example, Anthropic has signed a deal of 1 billion contract with Google to using their TPU and then set up the TPU cloud in their own infrastructure.
Oh wow. Okay, so that's how you know what the architecture is.
Oh, I see. So this architecture information is public.
Okay. Huh. Interesting. Do you know
Yes,
why they would make it public? Why would it be?
I think there are a couple of the papers. So this is a summarize of the knowledge that got captured from all the public paper from Google.
Okay.
And I was interning at Google as well, so I do know some internal information. And it turns out to showing that this public information has the same information as internal as well. So that's why we're creating this slide to serve as an encapsulator of all generation of TPU.
Okay. Cool. Thanks.
Of course, there is a new features from TPU as well, which I didn't cover. But these are maybe out of the scope for today's talk because we didn't utilize these new features.
Cool.
Yeah. Cool. So these hundreds of megabytes of last level cache will be shared by 1 or 2 tensor cores. And therefore, we call this last level cache as common memory or CMEM. And within each tensor core, we have tens of megabytes of local scratchpad. And this tens of megabytes of local scratchpad is organized into a vector of 128 lanes. And so we call them a vectorized memory, or VMEM. And within each lane, there are 8 sublanes. And each sublane has a local 32 instance of 32-bit register. And this gives us 1,024 local register files for each tensor core. And this gives us in total 100 of the kilobytes local registers. So putting all the memory in summary, TPU of various different generations give you around 100 gigabytes of off-chip HBM, as well as 100 of megabytes of on-chip memories. And further, TPU also offers massive compute. And each sublane has 2 local ALUs. And in total, each tensor core will have 2,084 ALUs. And these ALUs are designed to process vectorized operations, or vect op, as shown on the right. And so we call this a bunch of ALU together as VPU. And all these 2048 ALUs in the VPU work in the lockstep. That means whenever you start launching some workload into the chip, you have to utilize at least one ALU from all lanes and all sublanes together. Or in other words, every single instruction have to trigger a CMD of 128 by 8 ALUs. And this creating the granularity that we have to leverage to from the TPU to run on the realistic workload. And this VPU itself offers us 1 to 10 32-bit integer teraops. And further, each tensor core also contains 4 dedicated compute engines for matrix multiplication, and we call them as MXU. Each MXU is a 128 by 128 systolic array, which is designed to process large matrix multiplication. And this gives us 100 to 1,000 8-bit teraops for matrix multiplication. So if you're looking at the top flops difference from the matrix multiplication engine and vector arithmetic engine, you could observe one thing. The throughput for low precision matrix multiplication engine is about 100x higher than the high precision vectorized arithmetics. And therefore, we do want to use MXU as much as possible for higher performance. And lastly, TPU also have very abundant bandwidth for doing flexible reordering. Specifically, it has a dedicated unit called cross-link unit showing on the right, and which is also noted as SLU. And this unit could take the data from a vector of the VMAN and then reorder them and send it back. In other words, this SLU could do data reorganization at the granularity of VRAG level. And a VRAG here means all single register file from all the lanes together with all sublanes have to be issued in the CMD manner as well. And that's why we group one register file from all sublane together into a VRAG. That means every single data reorganization have to perform at the granularity of 128 by 8 32-bit registers. So putting all together, TPU has massive memory, sea of compute, as well as abundant bandwidth. And these features enable super fast primitives such as 32-bit vectorized addition, 32-bit vectorized multiplication, 8-bit matrix multiplication, as well as 32-bit transpose. But the question is, how do we use them for HE? In order to understand this question, we have to go through understanding the background of that. And then given the audience here are super expert on HE, so we will make it very short. First, HE will require a vector of floating point value if we using for CKKS scheme. And this 32,000 long vector data will be first encoded into a massive polynomial with tens of thousand degree, which we call as plaintext. And the degree of this is twice as the input length of the vector. And further, this plaintext is then encrypted into a pair polynomial of the same degree, which we call as ciphertext. And now let's look inside the ciphertext. Every coefficient in this ciphertext is an integer in the finite field. That means there is a limited range of the valid integer choice for we to pick. For example, if we have a modulus q equal to 14, then we could only take integers from 0 to 13. If a calculation results in a value that overflows this limit, for example, 12 plus 4, which exceeding the modulus value of 14, we need to call on a modular reduction to break it back within the range. And further, this restriction does not stop at the coefficient level. And each polynomial themselves is living in a ring. And just like coefficients has a limit, the polynomial has also a limit number of the degrees. And that degree value is usually a power of 2. So like here, we show you a n equal to 16 as an example. Each polynomial is a ring. That means when the polynomial exceeding their Happer limit of the degree value, such as 16 here, we need to call on a polynomial reduction to reduce it by the polynomial modulus to bring it within the range. In short, HE will bring both integer and polynomial modular reduction both vectorized operations as well as matrix multiplications. And further, even with RNS, HE also lifts the coefficients to 28 to 59-bit finite field integer. If we put the workload and compute together, then there is clearly compute and memory gaps. First, module reduction. HE requires module reduction, but the AI ASICs do not have it. Second, insufficient precision. Even with RNS, HE will still require 28 to 59-bit integer, but AI ASICs only support lower precision, such as 32-bit vectorized arithmetic and 8-bit matrix multiplication. And on the memory part, HE will require a data transpose or a data shuffling. Imagine that we got to do transpose or shuffling of a tens of thousand degree long vector. Putting the memory representation at such a big scale is very expensive, and therefore we want to get rid of them. So in Cross, we propose two compilation techniques: basis-aligned transformation to bridge the compute gap, and memory-aligned transformation to bridge the memory gap. The insight here is homomorphic encryption has pre-known parameter, such as the twiddle factor in NTT, and fixed computational graph. And this allows us to partially offload the HE workloads into the compile time. And then we can transform the remaining computation into the kernel that AI ASIC are very good at. So let's first talk about how basis-aligned transformation bridge the compute gap. And we will short the basis-aligned transformation as BAT. Given this 32-bit vectorized modular multiplication, A times B modular reduced by Q into Z, where we show each individual value here as 32-bit. For example, A, B, Q are all 32-bit as an example. And in realistic, Cross could tackle arbitrary precisions. And the basis-aligned transformation could lower this 32-bit vectorized modular reduction-based multiplication into two sets of kernels. First, low-precision matrix multiplication. And second, 32-bit vector addition. There is no module reduction needed at all. And within these two kernels, the first matrix multiplication performs A times B, and the second vectorized addition performs module reduction. Let's first dive into how A times B is converting into the first 8-bit matrix multiplication. We can take a pair from this 32-bit vector modular multiplication. For example, we take the first value, A0 times B0 into C0. And each of them, A0 and B0 are 32-bit. And the result C0 will be 64-bit. So our goal is to converting this high-precision scalar multiplication into low-precision matrix multiplication. Each high-precision value want to be computed in the low-precision manner. So we could just naively do a chunk decomposition. For example, a 32-bit input A0 could be broken into 4 8-bit chunks, as shown here, where we're using the superscript to indicating the chunk indices. For example, A0 upper 3 means the most significant byte, while the A0 upper 0 means the lowest or least significant byte. And we could apply the same decomposition for B0 and C0 as well. If we do this chunk decomposition, the original 32-bit high-precision scalar multiplication will be converting into this all-to-all multiplication of the low-precision chunk. And then if we want to compute it in temporal, then it takes 16 multiplications to generate all these 16 partial sums. And followed by that, we need to accumulate these partial sums back together, and then this will give us the results of C. If you really stare on this diagram, there's an interesting thing. For example, this A0, B0 is contributing to the lowest 2 byte of the C. For example, A00 times B00 is only contributed to the C00 as well as C01. And further, if you stare on the second a little bit lefter, A01 times B00 and A00 times B01, these two are only contributing to the second least significant byte, which is C01 and C02. In other words, from the rightmost to the leftmost, the basis is keeping increasing. So with this insight, the state-of-the-art GPU library could schedule this chunk-wise multiplication into a sparse matrix multiplication, where each row of these results indicating a partial sum with one basis. For example, this A00 will contribute into the least significant basis chunk, so they will be scheduled at the first row. And then the second rightmost rows are contributing to the second partial sum, which is have a higher basis, a bit higher than the first one. So based on this insight, people could repeatedly converting this left-hand side chunk-wise multiplication into a sparse matrix multiplication. And then all these partial sums will be shifted and accumulate together back to C0. But if you notice this structure, the left side matrix is most likely 0. It is actually a trouble's matrix of A, and half of the values are 0. That means we are performing redundant compute on half of the data. So to reduce this redundancy, we propose basis-aligned transformation for format that could eliminate this original sparse matrix multiplication into a smaller and dense matrix multiplication, shown on the right. Now let's see the beauty of the math behind it. The idea behind that comes from a simple observation. Block 2 in the matrix multiplication only contributing to the temporal partial sum, which I will show you here. First, these generated partial sums will be left shifted and accumulated into a 64-bit results. And these 64-bit results will be later on modular reduced by Q and become a 32-bit final results. This means the upper 32-bit part is only temporary value. Or in other words, the block 2 in the left matrix contributes only to this temporary part, which will be eventually fed back to the block 1. So if they only contribute the temporary part, could we directly offload them into compile time? That's what we did. Specifically, let's see how do we do by picking one pair of the data in the block 2. The overall result Z is equal to a summation of left shifted of all the partial sums, and then modular reduced by Q. And we keep our notice attention on the P sum 6 here. Specifically, P sum 6 is equal to A3 times B3. And we could further group A3 left shifted by 48 together. And then we can also insert a modular Q there. Before we do this, A3 is 8-bit, and 8-bit left shifted for 48-bit will become 56 bits. And that is definitely exceeding the 32-bit target. And after we bring this modular reduction Q into it, it can lowering this 56-bit higher precision scalar down to 32-bit, which we denote as R. And then we can chunk decompose this 32-bit R into different chunks. This allows us to get rid of this A3 from block 2 and then convert it back into block 1 by splitting different chunk of R back. And this is effectively aligns the basis of the value in the block 2 below 32-bit. And therefore, we call it as basis-aligned transformation. We could further repeatedly apply that to all elements in block 2 to feed them back to block 1 offline. And this will generate a smaller, dense matrix multiplication and giving 2x theoretical speedup. And now, original one's pair of 32-bit scalar multiplication could be lowered into this 8-bit k by k by times k by 1 matrix vector multiplication. And this will generate us a results of k by 1. So now we unveil the underlying math beauty of how do we converting A times B into the first 8-bit matrix multiplication. Let's now dive into the second pieces. How do we further lowering or reducing the mode reduction into pure vectorized addition? Now, we know we want to do A times B reduced by Q into Z. And then the first step already performs A times B into C. And then we apply back to one operand offline. So this converting this high precision scalar multiplication into a low precision matrix vector multiplication. Our second step is to accumulating these results back to C and then perform a modular reduction to convert or lower it back to Z. So let's starting with our eyes on the left-hand side matrix. With this left-hand side matrix, every single element in both left-hand side K by K matrix A and K by Y vector B are 8-bit. And the multiplication of two 8-bit value will give us 16-bit value. And further, this matrix multiplication will have a reduction of 4 elements. So an actual reduction of 4 16 value will give us a 18-bit partial sums. And these partial sums need to be accumulated by shifting and add. And to analyze this entire data as using 18 bits as underlying granularity isn't that obvious, isn't that direct. And therefore, let's changing our data representation. We could changing them into using 8 bits of 1 byte as underlying data representation. So these two are exactly the same. And we know all these temporal partial sums need to be accumulated together and then model reduced by Q finally into a 32-bit result. As you can imagine here, the upper 49 subtracted by 32, which is 17 bits, are also temporary. That means we only need to reduce these upper 17 bit elements. Or further boils down to the input, that means we only need to reduce the upper 2 highest significant byte, C4 and C5. If we know we want to only reduce the highest 2 byte, which is C4 and C5, that means our lowest 4 bytes could be stay intact. And this gives us the goal of modular reduce every single piece of data back to 32-bit. And given this lower 4 byte are already within 32-bit, so we just take them out and accumulate them by shift and addition. And here, I'm changing the shift of the 8 into the corresponding multiplication with the corresponding basis. For example,
can I ask a question? Like, I mean,
go ahead.
Wouldn't it be? I mean, when you leave the lower part intact and then you add these together, like it could still overflow your prime, right? So you don't necessarily get like full reduction, right?
Exactly, it is a lazy reduction, and then this lazy reduction will stay intact within 32-bit, so it will keeping always within the range of 32-bit without exceeding that. And then we could enable this lazy reduction throughout the entire program and only utilizing a full reduction in the end for the final result.
Yeah, I guess like a lot of the FHE algorithms actually use lazy reduction a lot because it benefits.
Yes.
It benefits throughout.
Yeah. Can't you get one additional bit when you do the addition and it'll go up to 33? And it's a small thing.
Yeah, you're right. So we are restricting on the prime value of the Q to 28 bits. And this will avoid having that one extra bit to overflow 32-bit. And then in fact, we also try 29-bit as well. And then based on our statistics trying, there is a randomness within encryption. So the actual value will not actually exceeding 3 more bits. Usually it will just need 3 bits. So you could also support 29 bits prime as well in reality.
Got it. Thank you.
Yeah, cool. So now we know that we want to reduce the high precision value down to 32-bit. And then now we just leaving the underlying 32-bit intact. We didn't change it. And then we multiply them with the corresponding basis and include them back there. And this will give us the original lower 32-bit value. So our attention will be how to focusing to reducing this highest 2 byte. First, let's take C4 as an example. We first converting this 8-bit C4 into this binary view. And then from the top to the bottom means we have the increase of the basis order. So 100101110. This will be multiplied with the corresponding basis and then accumulate back. So this 10 binary view of that will become this right line. And then the right-hand side, multiplication with the corresponding basis and the accumulation, these are values known ahead of time. And therefore, we could processing this higher than 32-bit value offline. And once we compute them offline, in the runtime or in the online, what we need to compute is just a log 2-bit value addition. They become just a vectorized addition. And we can apply the same trick to C5 as well. We first express this 8-bit C5 value into a binary view shown here, and then we pre-processing this basis offline to converting every single basis offset down to log 2q bit. And then in the runtime, we only need to accumulate this log 2q bit value together. And then we can merging all these tempers sum together to become the final Z. And it is a lazy reduction. In our current testing, if you have a Q less or equal than 28 bits, it will always 100% guarantee you will never exceeding 32 bit. And in reality, you could also try on 29 bit Q as well, because there is a statistic reason that most of this value will not exceeding for 3 bits more. So we testing among all various of the machine learning model, it can showing that 29 bits also works. And this,
to clarify, so
go ahead.
So I mean, this is not just using additions and multiplications. Like, it's really essential that you have these bit shifts on the TPU, right?
Oh, so on the left-hand side, this boundary lower 32-bit, we have this bit shift on TPU, and then it rely on vector processing unit to do the shifting and then do the addition. And then for the C4 and C5, we only utilizing this addition.
You're doing the shift now by multiplying those.
Yeah, I see. Okay. Yep.
Sounds good. Cool. Yeah. So now the high precision modularized multiplication could be lowered into only low precision matrix multiplication, as well as vector operation, which included the shift and add, as well as addition. The key insight behind this transformation is we can move the temporal results and runtime model reduction to compile time, because we just know this value of prime as well as a parameter ahead of time. So we don't need to bothering this computation to be online. With this, let's see how could we using that to lower a realistic workload. For example, high precision matrix multiplication, as shown here. Now we have a great friend, high precision matrix multiplication, showing on the top, which left-hand side matrix has H by V size, and this left-hand side matrix needs to be multiplied with the right-hand side matrix, but with the shape of V by W. And then this will give us the results of H by W matrix multiplication. And then this final result will be model reduced by Q. Within this matrix multiplication, every single element highlighting in the light blue here is log Q bit, which is ranging from 28 to 59 bit. And with that, we can just do a in-place transformation to converting each high precision scalar into a k by k low precision matrix and a k by 1 low precision vector. And this will directly lowering the original high precision matrix multiplication into low precision matrix multiplication. And this will enable us to using this high throughput of matrix multiplication engine within the TPU to accelerate this high precision matrix multiplication. And further, now we completing all the compute challenges. We no longer have compute challenges anymore, but we still have memory challenges. How do we gonna deal with this data transpose and data shuffling of tens of thousand degree long vector? That will bring us to the second contribution, memory aligned transformation, or short for MAT. First, let's tackle transpose. Let's starting with this transpose of matrix multiplication, where we have a parameter P need to be multiplied with a vector input to generate these temporal results. And these temporal results will be transposed into the final results. Of course, here is explicit transpose overhead. And our memory aligned transformation could embed this data transpose into the computational procedure itself. So here is how it works. Leveraging the linear algebra property, we could transpose this parameter P and inputs, and then we can offline transpose the parameter P such that this computation will directly generate the results as you expected. This could eliminate the explicit memory transpose into compute only. And further, for the data shuffling, we could apply the same trick as well. Let's starting with the example of shuffled matrix multiplication, where we have a same pre-known parameter P need to be multiplied with the input, and this matrix vector multiplication will generating a vector results. And these vector results will be shuffled into the final results, and of course, introducing shuffling overhead. And our memory aligned transformation could also embed this shuffling into compute. We could stay our eyes on the first row of white elements in the parameter P. We know this row of white will be multiplied with the input to generating the red element. And that red element is finally shuffled to the third location of the result. If we know this red element is targeting at the third location in the final result, then we can just shuffle the row of the pure white into the third row offline, such that this multiplication directly generates the results without paying any shuffling. And with this memory aligned transformation, let's also take an example to see how do we make the number theory transform a layout invariant operator. And all the audience here are known about NTT. We will skip this part. It could transforming the polynomial multiplication from quadratic cost into linear cost. And for parallel computing device, the most popular algorithm of NTT being used is called four-step NTT. Within four-step NTT, this input vector will first be transformed into a two-dimensional matrix. Here, I'm illustrating using 16 degree as an example, which will be lowered into a two-dimensional matrix of 4 by 4, which we're using R and C to indicating the row and columns. And this input matrix will go through 4 steps, as its name suggested. Step 1, we take this matrix and perform NTT of size R into every single column. Second step, we do a data transpose from the row major into column major. Third step, we do element-wise multiplication. And this will generating the results in the row major, in the column major, sorry. And then for this column major matrix, we're again doing the C input NTT to every single column. Now finishing this fourth step, we just do a base reverse of the results, which give us the final output. And within there, this entire fourth step NTT, you can see an explicit data transpose as well as an explicit bit reverse. So the way that math optimizes is shown on the following. We take the step 1 intact. We didn't change step 1. And then we remove transpose by transpose all the parameters in the following procedure. For example, we get rid of the transpose such that the parameter of the atomized multiplication will be transposed from the C by R into R by C. And then the third step, row-wise multiplication, will be swapped it and then transposed on the Twiddle factor. And we know the Twiddle factor is the symmetric matrix. So the transpose means do not do anything. And then we just have a layout invariant without doing transpose from these first 3 steps. And further, to get rid of the bit reverse, we could fabricate or factor the bit reverse into row-wise permutation as well as column-wise permutation into the parameter of both step 1 and step 3 shown here. After we do this row-wise permutation to the matrix in step 1 and column-wise permutation in the matrix of step 3, we can directly generate the results in the targeting layout form. And by doing these 2 transformations, we get rid of all the explicit memory transpose and make the entire NTT layout invariant. And in the end, want you to compute for NTT just matrix multiplication, element-wise multiplication, as well as matrix multiplication. Putting all together, let's see what performance of cross that we could give you. First, we built a Python TPU library for CKKS, an open source here, deployed in Google. And we're using kernel level workloads as benchmark, showing on the horizontal axis, and we compare that against the best FPGA as well as the best GPU, where every single vertical means the normalized throughput, where the best GPU's performance is highlighting in this 1.0 line, and every single bar is indicating the throughput value of cross. As you can see on the left-hand side chart, cross constantly achieving 9% to 47% higher throughput compared to the best GPU. And on the right-hand side, compared to the best FPGA, we are achieving a 2 order of magnitude higher throughput. That means cross turns TPU into the state-of-the-art throughput HE machine. So we could do a quick summarization of the cross. Cross turns TPU into state-of-the-art HE engine for HE kernels as well as HE operators. And they give you higher throughput and higher performance per watt than other commodity hardwares. And more importantly, cross redefines the capabilities of the AI ASICs. Previously, people think about AI ASIC could be only used for AI training as well as inference. But we proved that this AI ASIC has super strong matrix multiplication engine and vector arithmetics. And this capability could enable them to accelerate a more wider range of applications, such as modular arithmetics. And this project is fully open source and deployed in Google, and it also wins the second place University Demo GT Next Award Startup Creative X Zero launch. And we also gonna give a tutorial at us+. With that, we are perfectly time to move on to the second paper, which is how do we enable the AI ASIC to accelerate a more broader of the cryptography. Morph. Morph is also a joint work with Georgia Tech, Google, and MIT, and a special thanks to the Professor Sri Davadas, which is supporting our work. So this is targeting at the application of cryptocurrency, as well as verifiable encrypted computing. First of all, why we need to care about these two applications? It's because we have a super strong or largest market in that. The crypto market in the last year is overall giving you $3.5 trillion. It is the next largest market in the world. And even you consider a small portion of layer 2, itself gets 16 billion. So more importantly, this market is growing because of two trends. First, administration policy, such as Trump's administration has officially established stablecoin as official US dollars. So second, agentic systems. The emerging agent for doing crypto transaction and AI could be helpful, giving more throughput demand from this entire crypto market. And both these two growths, making the demand on the compute showing on the right curve, on the right-hand side figure. But to supporting this demand on the right curve, what we have today from Harvard is just showing on the dashed line. And you can see a clearly 10x throughput gap. That's why we build Morph, because we simply need more computing power. And Morph focusing on utilizing this new category of the powerful Harvard beast, AI ASIC, to accelerate zero-knowledge proof. What do we mean by zero-knowledge proof here? And for the expertise here, we could just make a very succinct introduction. In zero-knowledge proof, short for ZKP, a prover needs to convince a verifier that a statement is true, but without revealing any other underlying information. Considering a scenario where a prover wants to transfer all this verifier $1 trillion, and of course, the prover doesn't want to leak how much account balance does they have after they make this transaction. So what it could do is it can generate a zero-knowledge proof, which cryptographically protect the statement. And the verifier could only check whether it's true or false, but without knowing anything beyond that. This zero-knowledge proof is powerful, and checking this is really fast. It can happen in milliseconds, even with CPU. But the proof generation could be very slow. It takes hours, minutes, even days. So this proof generation limits the overall system throughput that become our acceleration target. And the reason why it is slow is coming from a high precision requirement. Let's compare that against HE. We know in HE we have 28 to 59 bits, but that will become 256 to 700 bits in zero-knowledge proof, which introducing a 10x higher demand. And further, this higher precision is working on the prime field. That means the modulus here showing on the Q is a prime value, which cannot be factored. So it invalidates the usage of residual number systems. Without this residual number system, RNS, the high precision multiplication could have to be lower into 16-bit chunk in order to tune with the Harvard machine word. And this high precision multiplication will become an all-to-all multiplication of these low precision chunks. If you have L different chunks, then in total you will pay L squared number of multiplication and give you a quadratic computation overhead. In other words, a 10x increase in the precision will introduce a 100x more computation demand. That's why make it very slower. And therefore, we make a solution to adding an extended non-prime field showing in red. Let's first encapsulate the original prime field showing on the F sub Q, highlighted in blue here. And what we propose is a non-prime field F sub M, where the modulus M here is non-prime value, which could be factored. And this enable us to wrap the entire computation happens in the original F sub Q into f sub m. For example, shown here, the value of a times b will generate a result of ab. And all of these will be within the range of m. Specifically, we choose the value of m to be larger than q squared, such that any multiplication will not exceed the value of m. And that enables us to perform this computation in the residual number system of f sub m, where we will have 2L number of the chunks. And this will lowering the quadratic computation cost into linear. So further, we can converting the results of AB back to f sub q, and then perform the module reduction there, and then convert it back to f sub m for the following computation. And this entire transformation could be scheduled as a low precision matrix multiplication. And that could be accelerated by the matrix multiplication available in the AI ASICs. And put this together, we also constructed an open source library, which is for TPU to enable ZKP primitives such as multiscalar multiplication as well as NTT. And compare with Cross, which we achieve up to 100x speed up under high precision crypto primitives such as MSM and NTT. And both make TPU also the state-of-the-art throughput machine for ZKP as well. And putting these together, in summary, I'm very thrilled today to introducing two lines of the compilation work, Cross and Morph, and both could turn TPU as state-of-the-art throughput machine for both homomorphic encryption as well as zero-knowledge proofs. And this positions AI ASIC as the state-of-the-art throughput machine for both low-precision crypto primitives as well as high-precision crypto primitives. So with that, I'm happy to answer any questions. And as a next step, I also want to prefetch, we want to enable the cross-kernel API into an end-to-end application, as well as build an entire Morph extended to support a full end-to-end protocol. And we are open for collaboration on how do we design a hardware-friendly protocol, or how do we align the Morph and Cross to support realistic applications from industry, such as the prestigious Microsoft research. Yeah, with that, I'm happy to answer any question.
Thank you, Yingming, for the nice presentation.
Thank you.